Last class you wrote number of relations from A to B. 2 raised to n of A cross B. Number of relations from A to B is 2 raised to n of A cross B. What do you mean by relation R on set A? Both sets are same. R is from A to A, or R is subset of A cross A. Relation R from A to A means R is subset of A cross A, or both the sets are same. Okay, so these things we studied last class, and we start now the class 12 topics, chapter 1, right? Chapter 1, relations and functions. Relations and functions. This chapter started in how many of your classes? Okay. Relations and functions. Subheading, equivalence relation. Equivalence relation. Subheading, equivalence relation. As I told you last class, you have to keep your notebook neat. If possible, you can prepare an index page with the chapter name, chapter content, page number. Okay, page number also you can put. And then date of starting. Today's date is 6, right? 6/2. And after writing the headings also, draw the lines like this. And left margin, here you can see in this page, there is a left margin, a small left margin also you can leave. Okay, like this, minute things if you keep, your notebook will be neat. Equivalence relation means a relation R on set A. R on set A is said to be an equivalence relation. R on set A means R is from A to A. It should satisfy 3 conditions. Number 1, reflexive. Number 2, symmetric. Number 3, transitive. I will explain each one. Okay, 3 conditions. First of all, we write a short note, then I will explain in detail. A relation, right? A relation R on set A. A relation R on set A is said to be an equivalence relation. An equivalence relation. A relation R on set A is said to be an equivalence relation if it is number 1, reflexive. Second condition, symmetric. And third condition, transitive. A relation R on set A is said to be an equivalence relation if it is reflexive, symmetric, and transitive. This is very important. R on set A. R on set A means R is from R on set A. Already you have written it in the introductory part. What is that? R is from A to A. There is no 2 different set. Both the sets will be same. R is from A to A. No, reflexive means every element, its reflection must be there. What do you mean by reflection? You look at mirror in the morning, right? What do you see? You see you only, right? Not other person, right? That is your reflection. That is called reflexive. 1, its image will be 1 itself. 2, its image will be 2 itself. That means If I write a set capital A is equal to set 1, 2, 3, 1, 2, 3, okay? Then R will be from A to A. R is from A to A means X elements will be from A, Y elements also will be from A. Then if it is reflexive, R must contain 1, 1, 2, 2 and 3, 3. That means every element, the same element must be there as the image for all elements. If I stop till 1, 1 and 2, 2, it is not reflexive. For all elements of capital A, its image must be there, okay? If it is 1, 2, 3, 4, if A is 1, 2, 3, 4, what should be the relation R? 1, 1, 2, 2, 3, 3 and 4, 4. Are you getting? Every element of R will be ordered pair because R is subset of A cross A. In A cross A, all elements are ordered pairs. So please write. This is the reflexive definition. Reflexive relation. Subheading. Reflexive relation. Right. If X comma X, its image is the same X comma X, element of R, element of the relation, for all X element of A, for all X element of A, for all X element of A, X comma X must be element of R, then R is reflexive, then R is reflexive, then R is reflexive. Example, you can write the same example. If A is set to 1, 2, 3, when you define every relation, there will be a basic set capital A, okay? Because R is subset of that A cross A. Then R, we can define if it is reflexive, the smallest reflexive relation will be like this. 1, 1, then what is that? 2, 2, 3, 3. We can add any number of elements, that is not a problem, but minimum these elements must be there for this one to be reflexive. And this is called the smallest reflexive relation on the set capital A. Is it clear, this writing? So this R is now reflexive. Means it's a reflection. For every element of capital A, its reflection must be there as the pair. Okay. Second, what is the second point for equivalence relation? Symmetric. Symmetric. I'll write the explanation. All right. Symmetric relation. Symmetric relation. If xy element of R, if it is given xy element of R, then its symmetric pair, reverse ordered pair. What is the reverse ordered pair? Yx, Yx. Okay, when you flip that one, we get Yx. Then if Yx is also element of R, then R will be a symmetric relation. If xy, if there is an xy element of R, then what should be there? Its reverse pair must be there. What is reverse pair? Yx also should be there. Then R is reflexive. Then R is, sorry, symmetric. R is symmetric. Then R is symmetric. Example, A is given again set to 1, 2, 3. 1, 2, 3, okay? Then I'm going to write R is equal to set 1, 1, 2, 2, 3, 3. If I write till here, it will be reflexive. Its reverse pair is 1, 1. It's 1, 1, 2, 2. It is 2, 2. That is understood. It is there. Okay, if I stop till here, it is reflexive and symmetric. But I add one more element, 1, 2. It is still reflexive, but it is not symmetric. Why? If 1, 2, if it is there, it's the reverse pair. What is the reverse pair of 1, 2? 2, 1 also must be there. Okay. If I stop here, it is now a symmetric relation. Is it clear? If there is a 1, 2, then 2, 1 must be there. If 2, 3, if it is there, if 2, 3, if it is there, then what should be there? 3, 2 also must be there. Understood? So then we write it is a symmetric relation. All of you understood? If there is an element xy, then it's reverse pair. Yxi, if it is there, it is symmetric. So got these two definitions clear? Reflexive and symmetric. What is the third point for equivalence relation? Transitive relation. Yes, please complete till here. Tarun finish till here. No, sorry, Jaden completed till this time. Muhammad Tanvir is there. Sharwin. Any doubt?
No, sir.
Third point is transitive relation. Transitive relation. Right. Transitive relation. This is the definition of transitive. If xy element of R and yz element of R. So look at the nature of these two. These two are given. Xy, then starting with the second element, y. Y is the element of R. Then, if these two are elements, then xz. Xz, if it is also an element of R, then we can say R is transitive. Okay, two elements will be given. Xy, then starting with that y. Y is an element of R, then what should be there? Then, if x is an element of R, we can write R is transitive. Okay. If xy element of R, y is an element of R, then if xz is also an element of R, we can write R is transitive. R is transitive. For example, did you write till here transitive? Example, if A is equal to set 1, 2, 3, A is equal to set 1, 2, 3. A is equal to set 1, 2, 3. Then I'm going to write an R. I'm going to make it reflexive 1, 1, 2, 2, 3, 3. It is reflexive. Then I will add an element 1, 2, and 2, 3. Is it transitive? Why? 1, 3 also should be there. 1, 2, and 2, 3, if it is there, then what should be there? 1, 3, yes. 1, 3 I have written. But at the same time, we check all other possibilities. 1, 3, and 3, 3, yes. 1, 3 is there. All connections we have to check. 1, 2, and 2, 2, yes. 1, 2 is there, right? 1, 2, and 2, 2. Starting with the y, all the pairs we have to check. Then 2, 3, and 3, 3. Yes, 2, 3, 2, 3 is there. Yes, it is there, right? Then 1, 3, and 3, 3. Yes, 1, 3 is there, right? So this is a transitive relation. Is it clear? So like this, for every xy and yz, if xz, if it is there in that pair or that relation, it is transitive. Got the points clear? Yes. Now for proving equivalence relation, we have to write the general forms like this. Any cases can be asked. We are going to start the questions based on that. For disproving, for not equivalence relation, we have to show any example which violates the rule. That is enough. For disproving, for proving that it is not equivalence relation. Yes. 1 minute, all of you please go through the definition equivalence relation. Your relation R on set A. R on set A. On set A means R is from A to A. is said to be an equivalence relation if it is, what are the three conditions? Reflexive, symmetric, and transitive. Yes, then what is reflexive? X comma X. It must be element of R. Okay, for all X element of capital A. Instead of this for all, a Greek sign is there in some question papers. That Greek sign is like this type of a Greek sign that represents for all. Okay, V and a cut. That's a Greek symbol for all. Instead of this for all, if this sign, if you see, that represents for all X element of capital. Yes. X comma X element of R. You understood that reflexive. 1, 1, 2, 2, 3, 3. If 1, 2, 3, if it is capital A. Then what is symmetric? If XY element of R, then it's reverse. What is reverse? Y, X is also element of R. It is symmetric. Then transitive means if XY element of R and Y is an element of R, then what should be there? Then if X is an element of R, R is transitive relation. R is transitive relation. Okay. Now let's start slowly the questions based on equivalence relation. It's right. Let T be the set of all triangles in a plane. Questions. Let capital T be the set of all triangles in a plane. Let capital T be the set of all triangles in a plane. R is a relation on T. R is a relation on T defined by R is a relation on T defined by R is equal to set of all ordered pair T1 comma T2 such that T1 is congruent to T2. Set of all ordered pair T1 comma T2 such that T1 is congruent to T2. Show that R is an equivalence relation. Show that R is an equivalence relation. Please write. Let T be the set of all triangles in a plane. Yes, please read it each and every part of the question. Let T be the set of all triangles in a plane, means T. It's in place of capital A, it is T. For every set, there will be a basic, okay, every relation, there will be a basic set like this. And R will be from that set to that set itself. R is from A to A. Here, R is from T to T, R on set to T. Are you getting? And what is this T? Set of all triangles in a plane. Triangles in plane means T will be like this. T1, T2, etc. So T is defined like this. Set of all triangles inside T. T1, T2, T3, etc. Like the set of all triangles in a plane are there in T. Okay, when we take the elements, we take it like this. T1, T2. T1 means a triangle. T2 is another triangle. Okay, and the relation connecting these. And how is it related? The relation T1 comma T2 will be an element of R. If T1 is congruent to T2. A condition is given for relation. That relation is all congruent triangles will be there as a pair in the relation. Are you getting? T1 is congruent to T2, then T1 comma T2 will be element of R. First of all, we have to prove that R is reflexive. R is reflexive. Okay. So the first step is to prove that R is reflexive. So reflexive. Reflexive proof is like this. We have to take an element from the basic set T. So let T1 element of T. T1 means a triangle. A triangle we have to pick from the basic set T. And for reflexive, every question you must have an idea of what you have to prove. Yes, what you have to prove for reflexive? For reflexive, we have to prove that in the reference space there is no problem for writing. Okay. Yes, what you have to prove for reflexive? X comma X is element of R. Here in place of X, I took T1, right? That means T1 comma T1 must be element of R. For that, according to the question, T1 comma T2 will be element of R if T1 is congruent to T2. Then when do we say T1 comma T1 element of R? T1 must be congruent to. Is it true for triangles? Every triangle, is it congruent to that triangle itself? Yes. Every triangle is congruent to itself. So we can write T1 is congruent to what? T1 is congruent to that triangle T1 itself. Are you getting? So we write the reason. Since, so this things we will write in the reference space. You will get an idea. Okay, we have to prove that T1 is congruent to T1. Its reason we will write in the main space. Yes, can you note down this in the reference space? For reflexive, what you have to prove? We prove that T1 comma T1 element of R. For that, we must show T1 must be congruent to T1 itself. Yes. Then to the main part we write, since every triangle is congruent to itself, since every triangle in a plane, since every triangle in a plane, plane means plane surface in a paper or in a board, okay, that is called a plane surface. Since every triangle in a plane is, yes, what's the point, children? Is congruent to itself, is congruent to itself. Yes, what do you write? T1 is congruent to T1. T1 is congruent to T1. Okay. Yes, that will give you the conclusion that T1 comma T1 element of R for all T1 element of T. T1 we took from T. The basic set is T. Alvin, the pair will be element of the relation. Okay, that elements we pick from the basic set, that is T here. Is it clear that writing is very important? In a style of writing is there like this for equivalence relation proof. Every step reflexive. This is the method of writing. Okay. Therefore, what do you write? Therefore, R is reflexive. Therefore, R is reflexive. Yes. Check the steps. All of you understood. You have to write 10 practices. Okay. So it's simple, but that style of writing you should follow each point. We pick an element from the basic set. For reflexive, always we start like this. One element we take from the given basic set. A basic set will be defined in the question. Okay, here it is, capital T. So we took T1. And in the reference space, you have written what you have to prove for reflexive. We prove that T1 is congruent to T1. Okay, so T1 is congruent to T1 since every triangle is congruent to that triangle itself. T1 is congruent to T1. So we write T1 comma T1 element of R. Okay, so R is for all. That also don't forget. For all T1 element of capital T. Therefore, R is reflexive. Yes, shall we start symmetric from online? Did you complete this reflexive proof? All of you completed reflexive part. All of you completed. Okay, next is symmetric. Symmetric. For symmetric, how many elements to be taken? Can you check the symmetric definition? 2 elements, correct, 2 elements. Because we assume x comma y element of R, then what do you have to prove for symmetric? Y comma x, it's reverse. Okay, we pick 2 elements. So I pick 2 elements. Not as ordered pair, we pick 2 elements means like this, T1 comma T2 element of where, from where do you pick the 2 elements? From T, and let the ordered pair, in relation all the elements are ordered pairs, and let ordered pair T1 comma T2 element of R. Then in the reference space you can note down. For symmetric, what do you have to prove? We have to prove that T2 comma T1 element of R, right? It's reverse pair, T2 comma T1 element of R. For that, what do you have to prove? For T2 comma T1 element of R, according to the given condition, T2 must be congruent to T1. Is it true from the condition given here? Yes. T1 comma T2 element of R means T1 is congruent to T2. Yes. If a triangle is congruent to another triangle, second triangle, then second triangle will be congruent to the first triangle. So from here we can write T2 is congruent to what? T2 is congruent to T1. Clear? So T1 is congruent to T2, and from there we write T2 is congruent to T1. And from here we can write like this, T2 comma T1, that is element of capital. Is it clear? Here we don't have to write for all. It is for a particular pair. So we stop till here. Then we write, therefore, R is symmetric. R is symmetric. Yes, please write symmetric. We can start symmetric like this. Let T1 comma T2 element of capital T. All of you please start symmetric. Let T1 comma T2 element of capital T, and let ordered pair T1 comma T2 element of capital R. Which means T1 is congruent to T2. If T1 is congruent to T2, we can write T2 is congruent to T1. T2 is congruent to T1. That means T2 comma T1 element of R. Therefore, R is symmetric. R is symmetric. Yes. So this is a pattern of doing symmetric. All of you understood. We pick 2 elements from the basic set and a pair. Assume a pair. That pair is like x comma y here, T1 comma T2. And we prove the reverse pair, which means T2 comma T1 is also element of R. Yes, please write. Next is transitive. Transitive. Third part is transitive. Yes, from online, did you complete this symmetric? Symmetric is done. Next is transitive, right? Third subdivision, transitive. Transitive, okay. For transitive, how many elements to be taken from the basic set, can you say? 3 elements. Already given. That is a given condition. Look at there. This is very important. T1 comma T2, it is element of R. If this condition satisfies, T1 is congruent to T2. Like this, every question, a particular condition will be given for that pair to be element of the relation. Some question it is like similar. T1 is similar. In some question, lines will be there. L1 is parallel to L2. Then L1 comma L2 L1. Some question perpendicular to will be there. Like that, or divisibility will be there. Mathematical conditions will be given. Okay, geometry or algebraic conditions will be given. Clear? Yes. Now, transitive, we take 3 elements and 2 assumptions. Transitive, can you recollect the definition of transitive? X, Y, Z after taking two pairs. What are the 2 pairs, Jaden? X, Y and Y, Z if it is. These 2 assumptions, then what do you have to prove? X, Z is element of capital R. Yes. So that's a style of writing. Let T1, T2, T3 element of capital T. From capital T, we pick 3 elements and 2 assumptions. And let, yes, what are the 2 assumptions? Ordered pair T1, T2 element of R and T2, T3 element of R. Okay, here also we can note down. For transitive, what we have to prove for transitive? We have to prove that T1, T3 element of R. T1, T3 element of R is. For that, what you have to get as a conclusion, T1 must be correct, congruent to T3. Yes, that we easily get from here. Yes, how to get T1 comma T2 element of R means T1 is congruent to what? T1 is congruent to T2 and yes, T2 comma T3 element of R means T2 is congruent to T3. T1 is congruent to T2 and T2 is congruent to T3. Is it clear? Yes. Now by combining these two, what can you write by combining these two? Correct. T1 is because a triangle is congruent to second triangle and that second triangle is congruent to third triangle. Then of course the first triangle is congruent to the third triangle. So by combining these two, we can write T1 is congruent to what? T3. So that will give you the conclusion that T1 comma T3 element of capital R. Therefore, R is transitive. Yes, please write transitive proof. Not simply writing, the style of writing you have to understand. How to take the elements from the basic set and what are the assumptions. Okay, by this question you got almost an idea. Okay, then you will connect it to the given condition in the question. Every question there will be a condition given for T1 comma T2, that pair to be element of R. Here the condition is T1 is congruent to T2. Then based on that condition, we will write the remaining. Then finally, the concluding sentence. What is the concluding sentence? You know, since R is reflexive, symmetric, and transitive, it is an equivalence relation. So like this, we'll write the concluding sentence. Since R is reflexive, symmetric, and transitive, it is an equivalence relation. Please write. Since R is reflexive, symmetric, and transitive, it is an equivalence relation. Since R is reflexive, symmetric, and transitive, it is an equivalence relation. Yes. So this is the completion of this first question. Clear? Yes. 1 minute, all of you please go through it. If any doubt in any of these steps, you can ask. If you understood this question, the remaining, okay, this style of questions will be so easy for you. So now please write the next question. Let L be the set of all capital L. So this is a basic set here. L be the set of all lines in a plane. Let L be the set of all lines in a plane and R be the relation on L. And R be the relation on L. And R be the relation on L defined by R is equal to set of all ordered pair L1 comma L2 such that L1 is perpendicular to L2. R is equal to set of all ordered pairs L1 comma L such that L1 is perpendicular to L2. Show that R is symmetric. Show that R is symmetric, but neither reflexive nor transitive. But neither reflexive nor transitive. Please write this question. Let L be the set of all lines in a plane. Last question T, it was set of all triangles in a plane. Here basic set is L. So L will be like this. In L, what will be the elements, you know? L1, L2, L3, etc. Like this, lines can be taken. L1, L2, L3, etc. Lines can be taken in a L. Okay? Set of all lines in a plane. And what is the condition given for L1, L2? That pair to be element of R? L1 must be perpendicular to L2. L1 to be perpendicular to L2. Then we have to prove that R is only symmetric, but R is not reflexive and R is not transitive. Okay. First of all, we check reflexive. We go in. That means it will not be an equivalence relation. The two conditions are not satisfying here. So for proving R is not reflexive, we will take an element. Always reflexive, we start like this. Let L1 element of capital L. Okay. And we have to prove that, yes, what we have to prove for reflexive L1 is L1 comma, we prove that here L1 comma L1 is not an element of R, right? Which means L1 should not be perpendicular to L1. Is it a truth as per geometry? A line, is it perpendicular to itself? No. A line, it can be parallel to, right? But it cannot be perpendicular to itself. A line cannot be perpendicular to itself. So what do you write? It is not L1 comma L1 is not an element of R, or L1 is or R is not reflexive. So please write there in the main part. Let L1 element of R. Since L1, a line is not perpendicular to itself. A line is not perpendicular to itself. A line is not perpendicular to itself. A line is not perpendicular to itself, which means L1 is, that is L1 is not perpendicular to L1, which means L1 is not perpendicular to L1. L1 is not perpendicular to L1. That means we write L1 comma L1 is, yes, L1 comma L1 is not an element of R. L1 comma L1 is not an element of R. Therefore, R is, yes, not reflexive. R is not reflexive. Yes, this is the first one for proving R is not reflexive. Is it clear? We take an element, L1 element of capital L. Since a line is not perpendicular to itself, L1 is not perpendicular to L1. That means L1 comma L1 is not an element of R. Next, we prove that it is symmetric. Yes, that is very easy. We take two elements, L1 comma L2 element of capital L, and let ordered pair L1 comma L2 element of what? Capital R, which means L1 is perpendicular to, can we say L2 is perpendicular to L1? Yes, yes. If a line is perpendicular to second line, that second line, L2 is perpendicular. So L2 comma L1 element of R. Can you write the same way? Right, symmetric. Symmetric. Yes, for symmetric, we have to pick an element, two elements. Let L1 comma L2 element of capital L. Let L1 comma L2 element of capital L. And let ordered pair L1 comma L2 element of R, and let ordered pair L1 comma L2 element of R, which means what can you write from here? The condition L1 is perpendicular to L2, and we can write if L1 is perpendicular to L2, L2 is perpendicular to L1. Here I am not writing in the rougher space. It is understood, right? Yes. So from here you will write that L2 comma L1 is an element of R. L2 comma L1 is an element of R. Therefore, R is symmetric. Therefore, R is symmetric. Yes. Hope you all understood this one. Yes, from online, did you complete? All of you finish? Reflexive is done, symmetric is done. What is the third part to be proved? It is not transitive. Okay, you know the style of writing. How many elements to be taken for transitivity? 3, L1, L2, L3, and 2 assumptions. What are the 2 assumptions? L1 comma L2 element of R and L2 comma L3 element of R. And we prove that L1 comma L3, here it is not an element of R. Yes, so let's start. Transitive. Transitive. Yes, we start with the 3 elements. Let L1, L2, L3 element of capital L, and let the ordered pair L1, L2 element of and L2, L3, which is element of R. L2, L3 element of R. Yes. L1, L2 element of R means L1 is perpendicular to L2 and L2 is perpendicular to L3. L2 is perpendicular to L3. Yes. By combining these two, can we write L1 is perpendicular to L3? So we have to check that one. Here L1, this is L1. L1 is perpendicular to what? L2, this is L2. L1 is perpendicular to L2, okay? And L2 is perpendicular to what? L3. Then what can you say about these two? Are these perpendicular? No, instead they are parallel. They are parallel. Are you getting the point clear? So L1 is not perpendicular to L3 and it is parallel. So can you draw that one? That picture will help you to understand it faster. This is in plane. This one clearly given in plane. Plane is clear. That is what clearly defined. This type of questions are defined in plane. Plane is only 2D, a normal paper or a board. Okay. Yes. But L1 is only parallel to L3. This is parallel to L3. Okay. So that will give you the conclusion that L1 comma L3 is not an element of R. L1 comma L3 is not an element of R. Therefore, R is not transitive. R is not transitive. Is it clear? R is not transitive. Okay, so this is the completion of this question. Next is a very important question for MCQ. Right, an MCQ in between. Can I leave for 10 minutes? Oh, okay. Tanvir, it is not at fine. No problem. Right. R is equal to relation R is given like this. Set of all ordered pair X comma Y such that X is brother of Y. X is brother of Y. X is brother of Y. Is R a symmetric relation? Which is right. R is equal to set of all X, Y such that X is brother of Y. Is R a symmetric relation? What is your opinion? Symmetric relation means YX also must be element of R.
Yes.
Hmm?
Yes.
Any difference of opinion?
Yes, sir. Why can be sister?
Sister of X. Anyone sitting here with a sister? Do you have a sister?
Yes.
What is the name of your sister?
Disha.
Disha, okay. Srinigesh is brother of Disha. In place of X, it is Srinigesh, right? Srinigesh is a brother of, that is X, brother of Diksha. This is Y. Okay, then YX will be element, Y will be brother of X. Is it? No. Disha is sister of Srinigesh. That means Y can be, if it is a male, then it is okay, right? But Y can be a male or female, right? If Y is a female, Y will be the sister. So it is not symmetric relation. It was there in a past paper. Okay, so please write. Here R is not symmetric. Write the answer. R is not symmetric. R is not symmetric. Reason XY, element of R, does not imply that YX element of R. Does not imply that YX element of R. Because Y can be sister of X. Because Y can be what? Y can be sister of X. Y can be sister of X. Please note down. R is not symmetric. Because XY element of R does not imply that YX element of R. Because Y can be sister of X. Is that clear? Please note down. Which one?
The one you want.
This and then?
No.
Brother of. Short form, brother of. Examination should not write this example, okay? Just YX, don't write Srinigesh, right? Like that. Next is. Maybe you understood that, right? Like this, you have to connect it to the real life situations, those type of questions. You will easily get the idea, okay? So relations means it can be anything, not only mathematical relations, it can be human relations also, okay? So that way also questions can be asked. Next, some relations are trivially transitive. Trivially transitive means normally transitive, how do you check transitive? XY, then YZ. Okay, suppose only XY. XY is given in a relation. It is a transitive because there is no pair starting with Y for checking further. So that type of relations are trivially transitive. Are you getting? If there is only XY element of R, it is trivially transitive because there is no ordered pair for checking further. So please write a special note. A special note. Let A is equal to set XYZ and R is equal to ordered pair XY. Ordered pair XY. Then R is trivially transitive. Trivially transitive because there is no ordered pair starting with Y for further checking. Okay, that is called a trivially transitive. Then R is trivially transitive because there is no ordered pair starting with Y for further checking. But is it symmetric? No, it is not symmetric. For symmetric, if XY, then what should be there as element of R? YX should be there. It is not transitive. Is it a reflex? It is not symmetric. Sorry, it is not symmetric. Is it reflexive? No. Reflexive minimum 3 pairs must be there. If A is X, Y, Z, what are the minimum 3 pairs should be there for a XX, then YY and Z must be there, okay? Yes. So you can,
Start with the curly bracket.
because our relation always a set. Relation is a set of ordered pairs because it is subset of A cross A.
No, sir, then why
Oh.
do you edit it? Count that.
You are asking, oh, sorry, this is wrong. So you will correct it. Okay, fine. Next is a simple definition. After that, we start another question. Yes, did you complete this one? Yes. Next definition, after taking attendance, I will write the next one. By that time, please go through these things. 1 minute break. After that, we'll start. Yes, attendance. Aaron Kyriakos. Afra.
Present, sir.
Alvin. Aman. Anirudh.
Present.
David.
Present.
Jaden. Lanston. Muhammad Tanvir. Nathan. Rachel.
Present, sir.
Sherwin. Srinigesh.
Present, sir.
Denvin. Next, you please write the subheading equivalence class. Equivalence class. Subheading equivalence class. Equivalence class. So please write the explanation, then I will explain it. Let R be let capital R be an equivalence relation. Let capital R be an equivalence relation on a set A. On a set A, and let small letter a an element of capital A. Small letter a an element of capital A. Full stop. Next line. The set of all those elements of A, the set of all those elements of A the set of all those elements of A which are related to small letter a. In bracket we write X is related to small letter a. X capital R A, which means X is related to small letter a. The set of all those elements of capital A which are related to small letter a, which means we find X that is related to small letter a, is called the equivalence class of A. Is called the equivalence class of A. Equivalence class of A. Please write that sentence. The set of all those elements of capital A which are related to small letter a. That means X is related to small letter a is called the equivalence class of A. Equivalence class of A. Equivalence class of A. It is denoted by, next slide, it is denoted by like this. In a square bracket we write a small letter a. It is denoted by, in a square bracket we will write a small letter a. It is denoted by, like this. In a square bracket we have tried small letter a. Next line we write like this. X is related to A means X comma Y element of capital R. This is called X is related to R. X is related to A. X is related to A means X comma, not Y, sorry, A. X comma A. X comma A element of capital R. X is related to A. That means in place of Y, it will be A. X comma A element of capital R. Then that values of X are called the equivalence class of A. Equivalence class. That means elements which are related to that A. For example, A is given set 1, 2, 3, 4. And then it should be an equivalence relation. So I write simply an R. 1, 1 is there, 2, 2 is there, 3, 3 is there, and 4, 4 is there. Okay, 4, 4 is there. Okay, then I add some more elements. I add some more elements like 1, 3, then 3, 4. If 1, 3 and 3, 4 are there, then what should be there? 1, 4 must be there, right? 1, 4 must be there for a transitive. Then 3, 1 must be there for symmetric, and which should be there. 4, 3 must be there for and 4, 1 also must be there for symmetric. 4, 1 must be there for symmetric. Still we have to check with other pairs. 4, 3, yes, it is there. Okay, so now this is an equivalence relation. because it is reflexive, symmetric, and transitive. Now I'm going to write equivalence class of 1 for this one. Equivalence class of 1. Equivalence class of 1 means elements which are related to 1. Yes, what are the elements related to 1? 1 is there. That means 1 should be there in place of y. Okay, 1 should be there in place of y. Yes, 1 in place of y. In what all elements we can see? 1 in place of y. Then which one? 3 1 is there. Okay, then which one? 4 1. Okay, then from these pairs we collect the x elements. Only x elements. Yes, what are the x for these pairs? 1, then 3, and then 4. That collection is called, that x values are called the equivalence class of 1. Are you getting the point clear? X element of x, the values of x which are related to A, that is called equivalence class of A. That means equivalence class of 1 in this one will be 1, then 3, and 4. It is not an ordered pair, it will be a set. This will be a set. Now you got the idea of equivalence class. Now once again, please go through the definition and the example, clearly that example. Yes, did you write this example? Now once again to the definition. For equivalence class, R must be an equivalence relation. That is the number one condition. So let R be an equivalence relation on a set capital A. On a set capital A means R is from A to A. It is there everywhere. In every relation in this class 12, R on set A is there. Means there is no separate set A and B. R is from A to A. Let small letter A element of capital A. Okay, here I took an element like 1. 1 is element of capital A, like small letter A element of capital A. Then the set of all elements of capital A, which are related to small letter A. That means all X collections we have to find. All X which are related to small letter A. Related to small letter A means X comma A element of capital R. That X values are called, what do you call that one? Equivalence class of A. Is it clear? It is denoted by, like this in a square bracket, we write a small letter. Now all of you understood that one? The values of X. And that is what example we have written like this. Elements which are related to 1. Okay. So we wrote like this. Now same way, can you say equivalence class of 3 from the above example? What is equivalence class of 3? Equivalence class of 3 from the same example? 3, no. 1, correct. 3, 1, 4. 3, 1, 4. That means for these pairs, you can see 3, 3. In this one, 3 we take because it is related to 3. Then 1, 3 we take 1, and 4, 3 we take 4. Okay, so that is the equivalence class of 3. Clear? So equivalence class definition, hope you all understood. Yes. Now I just write a question. Okay, it's a detailed explanation. We'll be doing it next class only because I have to go little bit early. Okay, to the school in between I have to go. So I will write the detailed explanation of the next question in the next class. Okay, so we write the question today. Okay, we write the question. In that one, equivalence class is a part. It's a 5-marker question. Okay, if I start also, I cannot finish it today itself. In this chapter, from this chapter, in every question paper, there will be a 5-marker question. All of you know, in board examination, we have 4 5-markers. Out of this, first 5-marker is from this chapter. Okay, every board exam paper, 1 5-marker is from chapter 1, relations and functions. Okay, so this is a 5-marker question. Right. Show that the relation, write this question, it is a 5-marker question. Show that the relation R on set Z of integers R on set Z. What is Z stands for, integers. Z is for integers. In class 11, we have studied the important set notations. Z is for integers. Okay. R on set Z of integers given by, show that the relation R on set Z of integers given by R is equal to set of all ordered pair A comma B such that A minus B is a multiple of 2. A minus B is a multiple of 2. A minus B is a multiple of 2. Is an equivalence relation. Is an equivalence relation. Is an equivalence relation. That is the first part. Then second part is also find the elements which are related to 1. Also find the elements which are related to 1, or this part can be asked like this also, or find the equivalence class of 1, or find the equivalence class of 1. Both have the same meaning. Equivalence class of 1. Okay, equivalence class of 1 means elements which are related to 1, X elements which are related to 1. So both are of the same meaning. So one of these ways that additional part will be asked. Okay, I'll give you an idea of this one, how to prove. The first part, I think you can easily try and write. Okay, first part, we have to prove 3 headings. What are the 3 subheadings for equivalence relation? Reflexive, symmetric, and transitive. Okay, for reflexive, you will prove A comma A. Here, instead of X comma X, we use A. So we take A from the basic set. Basic set is Z. So reflexive, we start like this. Let small letter A element of capital Z. And we prove that A comma A element of capital R. For that, what do you have to prove? A minus, in place of B, what should be there? A. What is A minus A? 0 is a multiple of 2. 0 is multiple of any number, is correct. So A minus A is 0, which is a multiple